Welcome viewers, my name is Engineer Baga. Today we have a topic before us, eccentrically loaded footing. In our last video we talked about axially loaded footing and we were able to design an axially loaded footing using the Bs8110. Today we are going to continue in design of footing. At this time we are treating eccentrically loaded footing. If you are new to this channel, please do wait to hit the subscribe button. I'll see you. Look at how to design a footing that is eccentrically loaded. Now, what do we mean by eccentrically loaded footing? Eccentrically loaded footing, they are basically footings that are subject to axial load and moment. The moment could either be uniaxial moment or biaxial moment. But today we are going to concentrate on uniaxial moment. Now, eccentric footing could also be a footing that is subject to only axial load, but the footing, the column is placed at an eccentricity from the centroid of the footing. All right. So when you have a system whereby you have a footing where the column is placed not at the center but at an eccentricity from the center of the footing, that kind of design will result to an eccentrically loaded footing of the column. Now, if we have that situation, we are going to have an eccentricity, the total resultant load, and it's not going to lie on that center. Okay, so this can result to an eccentrically loaded footing. All right, this is on our question today. We have our moment, which is the uniaxial moment. We have the service moment, and we have the ultimate moment. The service moment will be used for the sizing of the footing, just as we use the service axial load for the sizing of the footing. The bearing capacity has been given in the formula, and then we have the characteristic strength of material FCU 25 Newton millimeter square, and the strength of steel to be 410 Newton millimeter square. All right, so we can go ahead and solve this problem. All right, so let's look at the load acting on the footing. Now we have the total dead load to be 650 kilonewton. We have the live load to be 350 kilonewton. Let's assume the footing own weight to be equal to 15% of the total dead load from gravity load. And if we do that, we are going to have 15% of that footing weight to be 97.5 kilonewton. Now, having gotten the dead load due to the footing weight, we're going to factor that dead load. But first of all, let's calculate the total service total dead load. Now, if we add 15% of the dead load into the total dead load, we're going to have it as have it to be 650 plus 97.5. We'll have it to be 745 kilonewton as the total dead load that is acting on the footing. Now we need to get that total service load and total ultimate load. So we said that the total ultimate load from BS8110, we have the partial factor of safety 1.4 for dead load and 1.6 for live load. So we should have the total load to be 1,606.5 kilonewton as the total ultimate load. While we have the total service load on the footing to be 1.0 GK plus 1.0 QK, we have that total service load to be 1097.5 kilonewton. Okay, so having gotten these two load, remember that in sizing of the footing, we make use of the total service load of the footing. Now, if you look at the question, you will see that the footing is subjected to a column that is axially loaded, and it has a uniaxial bending. So we have the column to be axially loaded column with a uniaxial bending in the x direction. The moment due to service load of that column has been gotten. We have it to be 50 kilonewton meters. And equally, we have the moment due to ultimate load of that footing. We've got it to be 85 kilonewton meters as the moment due to ultimate load. All right. So these are the two loads that are applied now. we have the ultimate load under ultimate limit state. We have the ultimate load to be 1606.5. We have the service load to be 1097.5 kilonewton. Now, we have these two cases. Remember that we said that we need to size this footing. Now, in doing that, remember we have our punching shear requirement, that our punching shear, for stability purpose, our punching shear, the breadth of our footing should be greater than the column size, which is one side of the column plus 3h. All right, that is the punching shear requirement. Now, I said for a rectangular footing, we should have the length to be greater than the breadth, while for a square footing, we should have the length to be equal to the breadth. All right, so we are saying, okay, we have the breadth of this footing. We're going to decide, let's do it a rectangular footing, a square footing, right? Let's do it as a square footing. So if we are doing it as a square footing, we have the breadth to be greater than the column size. We have a 225 by 225 column. We have plus 3h. Remember that 3h is the distance of the critical, the distance of the column to the end of the critical perimeter on both sides of the critical perimeter. All right, according to our codes. So if we add 1.5h plus 1.5h, it will give us 3h. So we are saying that this breadth of footing should be such that it should be greater than the critical perimeter, the width or the breadth of the critical perimeter of the footing. All right. So based on that criteria, for us to have this thing to be stable, we are going to choose a footing of thickness 400 millimeter as our depth of footing. Okay, so if we do that, we're going to have that the breadth of the footing should be greater than 1425 millimeter. Okay, so now having gotten to this point, we need to choose a value for our footing. All right, now if we look at the board, you will see why it is necessary for your breadth of footing to be greater than your column size plus 3h. Let's just take a look. We have already chosen a breadth of 200 mm. Let's take a breadth of 200 mm, but let me explain further why the breadth of your footing should be greater than your column size plus 3h. All right, so why is it essential? All right, so why is it essential for your breadth of footing to be greater than your column size plus 3h? Now, we know from the code we have from this point, here to our critical perimeter to be 1.5h. And what we are saying is that if you want to choose a breadth, if this line represents our critical perimeter, if you want to choose a breadth of footing, you must ensure that that breadth of footing is above this critical perimeter, because the failure point, the failure of the footing, the punching will start from this whole place. This whole entity where we have this circle will punch out of the entire footing. So in a case where you don't have your footing extended, it makes it much easier for this old stuff to sink into the soil. And that is the diagram I'm trying to illustrate here. You can see that this is the area, this is where we have the critical perimeter, from the column to where we have the critical perimeter is 1.5h. We have it this other side 1.5h. So when this load, the axial load comes on it, it pushes the whole stuff down to the soil. If the soil bearing capacity is not enough to resist, you are going to have this whole thing sinking down into the soil. All right, so we are saying that if you must choose a breadth B, you must ensure that your B is greater than K, where K represents this distance, which represents from here to here represent, this boundary represents our critical perimeter. That is the area inside the critical perimeter. Okay, so that is what we are trying to say. So if you look at it, we have here K, which is the area representing the area within the critical perimeter, which is the whole of this circle. So your footing breadth should be greater than this. So I said that the K should be, our K represents our column size plus 3H. In this case, our column size is 225 plus 225 by 225. So we say 225 plus 3H, where we have here to be 1.5H, 1.5H. So if you add both of them, it becomes 3H. Okay, so we are saying that the breadth of the footing must be greater than K for the footing to be stable, so that it will meet stability requirement. All right, so that is one. So that is why we are saying that B should be greater than the column size plus 3H. Now the next thing we want to do is to calculate the maximum resultant load. Now, for eccentric footing, what makes it eccentric is that the resultant vertical load acts at an eccentricity away from the centroid of the footing. Now, for a rectangular footing, or rather, let's take a rectangular footing. Let's assume we are dealing with a rectangular footing now. For a rectangular footing of this nature, the center of it, we have here to be L over 2, L over 2. So that represents the center. So how do we calculate the eccentricity? N represents the vertical load that is acting on the footing. All right, so now have a look at it now. We can say that the total gravity load that is coming on this footing N, let's call the total gravity load N. Now, when this gravity load comes on this footing, we equally have another applied load, which is a moment, mx, under serviceability condition. Now, this moment, together with this axial vertical load, is going to produce an eccentricity of the resultant load. The resultant vertical load, let's call the resultant vertical load RL. All right. Now, for us to get the resultant vertical load, we have to add the total vertical load. Of course, we have just one vertical load acting at the centroid of the footing, which is N. So it means that our resultant vertical load will be the same as N. Okay? Now, because of the presence of bending moment in one axis, we are going to have an eccentricity of the resultant vertical load, RL. Now, the eccentricity is going to be the distance of the line of action of the resultant load from the centroid of the footing. Now, that distance is what we call the eccentricity of the resultant load on the footing. We call it Ex. So if the eccentricity is Ex, which means the eccentricity in the x-axis, the resultant load is likely to act on the left-hand side of the centroid. Now remember, this is our centroid position. Let's assume that the resultant load is acting on this direction. We do not know the direction it's going to act, whether it's going to act on this side or is going to act on our left-hand side where we have it now. But when you are solving this problem, you can put your resultant load in any direction, either on this side, which is our Q side, or you put it on our Z side. Whichever you want to put it is okay. The sign convention will correct it if it's in the wrong direction. Okay? So in this case, I want to put my RL, which is my resultant load, on this direction. At an eccentricity which I do not know, let me call it Ex from the centroid, where we have the normal load acting. And we have the breadth of the footing, which is the total breadth, B. So From the center of the footing, we'll have B over 2, B over 2. Now, remember, we've already chosen the footing to be 2 meters, so let's leave the numerical value first. Now, we'll say the total vertical resultant load, let's call it RL. All right? And we said that that total vertical load is the same thing as the total axial load on the column. Now, let's take a summation of moment about the center of the footing so that we can obtain our eccentricity, EX. If we take a moment about O, we have RL, which is our unknown resultant load. We've known it now to be N. We have it to be RL times EX. RL times EX, it gives us an anticlockwise moment. And we have MX, which is our applied moment, is the clockwise moment, so we have it. So sum of moment, clockwise moment equal to sum of anticlockwise moment. So we have RL times EX is equal to MX. All right. So the next stage is to look for our eccentricity EX. When we solve for EX, we'll have that EX becomes our applied moment MX over our resultant load RL. Of course, we know that we'll find out that our RL is the same thing as our N, which is our axial load. But in a case, like in the case of combined footing, of course, you will know, you discover that your RL will be different from that particular, your RL becomes the summation of the load for the two columns in the case of a combined footing. Okay? So with RL in this case, we say it's equal to N. Applied moment mx under serviceability state is 50. So if we do that, we are going to have 50 over the applied load under serviceability limit state also. We'll have that eccentricity to be 0.045 meters. Okay? So this is the eccentricity we have. So what we are saying is that from the center of the footing to where the resultant load, the line of action of the resultant load is 0.045 meters. So that represents our eccentricity. Okay? So normally, from your layman's view, you think the load is acting at the center of the footing according to your plan, but because of the presence of moment, which is a uniaxial moment, you have some eccentricity. Now, in some cases, the moment could be biaxial moment, especially for edge columns. When the moment becomes a biaxial moment, of course, we are going to be calculating it in a different method, using a different formula. All right? So, but today we want to look at uniaxial bending. Now, the next stage after we've gotten our eccentricity is to proportion our footing. Like I said, for stability requirements, the stress due to service load should be lesser than the allowable soil bearing capacity of the soil. Now, the stress due to service load is going to be two stresses. We're going to have stress due to direct load, which is axial load, where that stress becomes the load over the area. Then we have plus stress due to compression. Compression zone is the zone where we have the resultant force acting. So if we want to take the compression zone, it's from 0 to Z. So we're going to have it as positive. So we have M over our sectional modulus of the section. Of course, remember from your strength of material that sectional modulus is equal to moment of inertia of the section over the centroid to the fiber that we're interested in. Okay? So in the case of this, we have our y, moment of inertia. We have our sectional modulus z is equal to I over our y, where y represents the distance from here down to here, from here down to here, which is our breadth, b over 2, our breadth, which represents the breadth of the footing, we'll now have it as B over 2. B over 2. Okay? So that represents our breadth. So if we apply the formula correctly, now we're going to have M over Z over XX, sectional modulus with respect to the x-axis. And if we do that, we know what that is. That sectional modulus with respect to the s-axis becomes moment of inertia with respect to s-axis over y. This y is our B over 2. Okay? That is the centroid to the bottom of the plate. So we said that. Now the area A is the breadth of the footing times the length of the footing. Or in the case of a square footing, we have the breadth times the breadth. So if we solve and look for the moment of inertia from this formula, we'll have that the moment of inertia Ixx is equal to the length in the case of a rectangular footing over the breadth raised to power 3 over 12. So that will give us our I. So all we need to do is to divide our I by B over 2, which represents our Y. Okay? So that we'll have two stresses acting on this footing. When we do this, N over A plus Mx over Z, we'll have a stress around the zone where we have the resultant load. And that is from this zone here. We have a bending stress, which is a compressive stress. It's positive. Now on this other side of it, which is our 0 to Q side, we are going to have a negative bending effect. And that negative bending effect, if we divide it by sectional modulus, we are going to have it on this other direction. Now, I said that the moment at this point is not our applied moment. This M is not our applied moment. This M is a moment due to eccentricity of the resultant load. If we already have our resultant load to be 1097.5, it means that the moment due produced about the center of the footing becomes the resultant load times our eccentricity. Of course, we know our resultant load is the same as our axial load, so we have our axial load times eccentricity. Okay? So we have established this. Now let's go over and let's apply the values to this problem. We have the moment to be equal to the resultant load times eccentricity, which is the same thing as the axial load times eccentricity. The area is BL, B times L, or B is B if it's a square footing. The moment of inertia, if it's a rectangular footing, is B squared raised to power 3 over 12. But if it's a square footing, it becomes B times B raised to power 3 over 12. So whichever you are working on, you can apply the formula conveniently. All right. So having known this, I believe we can be able to analyze the pressure variation, which represent our base reactive pressure for this footing. Now let's go over and let's calculate these stresses. We'll calculate the stress on this side Z. We'll calculate the stress on this side Q. So this is the side we have our resultant. So we're going to have more stress on this 0 to Z axis compared to 0 to Q axis because of the more loads are acting on this direction. Now, if the resultant load continues to move towards Z, the eccentricity increases, and if that happens, this part of the footing begin to lose pressure. There will be lesser pressure on this direction, and that might result to what we call loss of contact pressure. What it means is that the concrete footing, the pressure on the concrete footing on this zone becomes very, very minimal. In some cases, at the edge here, you might have zero pressure, or at certain distance, you might have no pressure at all. All right? So that results in what we call loss of contact pressure. Okay? So now let's go over and let's work on this. Sectional modulus I, because sectional modulus becomes moment of inertia over a centroid from the neutral axis. So if we have the center from the neutral axis to be 1, to be B/2, which is going to have this to be B/2 divided. We have this. We now have our sectional modulus to be B⁻³ equally, the moment the moment becomes we've got the moment to be NE. So NE divided by our sectional modulus, we have it to be 6E/B². Okay. Now the next thing we have is the stresses acting at the ends of the footing. We have the stress. Of course, we know what our M/Z is. Our M/Z becomes this. So we have the expression simplified to this point. So if we factorize it, we have this. So we can now say that our stress, both the maximum and the minimum stress under serviceability condition, you can see that we're applying a service load, and our dimension, we've chosen dimension of a 2 meter by 2 meter. So we're having 2 meter by 2 meter. So let's check if 2 meter by 2 meter will be adequate for the soil. When we do that, we're going to have the maximum stress to be 311.4 kilonewton per meter square, and that stress is not lesser than the allowable soil pressure of 200 kilonewton per meter square, which is the soil bearing capacity. So based on that, we have problem with our choosing dimension for this footing. Now, if you see, we have the minimum stress, which is okay. The minimum stress is greater than 0, which is okay. We don't have problem with the minimum stress, but the maximum stress, we have some issues. So if that is the case, it means we are going to increase the size of the footing by choosing a new dimension for the footing. So I have chosen 2500 mm by 2500 mm as the size of this footing. Now, of course, we can check that using the same principle, checking the stress due to this size. If we do that, we are going to have the maximum stress to be 194.5 kilonewton per meter square, and it's lesser than the allowable soil bearing capacity of 200. So we said it is okay. Of course, if that is okay, we know that the minimum is equally okay. All right. So we can boldly say that our choosing dimension of 2.5 meter by 2.5 meter is adequate for stability for this footing. Now, apart from this method of checking the soil bearing uh, limit, we can decide to also size the footing by using the soil bearing capacity. Like I will say that we can say that the maximum load, we can say that the maximum stress is less than 200 kilonewton per meter square, which represents our soil bearing capacity. If we fix in the breadth of the footing, we solve that equation, we're going to have the breadth to be equal to 2.3. Divide this 1097 divided by 200 and take the square root. We're going to have 2.3. So we can now have that the breadth of footing B must be greater or equal to 2.3 meters. Okay. So if you have that, you can choose values from 2.3 meters for your size of footing. This is a square footing we are dealing with. Okay. So if you decide not to go through this process, you can make do with that to obtain the required dimension for our footing. Okay. So now we've been able to size the footing. The next step we will want to do is to carry out the necessary check. First of all, we'd like to start with our punching shear check. We'll check for the punching shear. Then next we'll check for the transverse shear. After which we go on with the design for reinforcement. All right. So now let's go over to the punching shear check. First phase we are going to look at is the loading and the design of the footing itself. Now we've seen that we've been able to size it accurately. Now we have the ultimate load to be 1606 kilonewton, and we have the ultimate bending moment at the column to be 85 kilonewton meter. That is a uniaxial bending. So from there, we can obtain the eccentricity of that load like we did in the previous case of service load. we'll have it to be 0.0525 meters. And applying our formula for a maximum and minimum pressure at the two extreme ends of the footing, we have the pressures to be 289.33 kilonewton per meter square and 224.58 kilonewton per meter square. So these are the maximum and the minimum pressure at the two extreme end of our footing. Okay. Now, having done that, we need to obtain other loads. For example, we have a surcharge load. Surcharge load are usually life load on the surface of the building. Right, so let's consider other load that are going to be acting on this footing. Now we have a surcharge load. Surcharge load are usually life load. So let's call it QK equal to 5.0 kilonewton per meter square. And we equally have the dead load. The first load is the load due to our mass concrete slab of 150 mm. And we have the unit weight of the soil to be 18 kilonewton per meter per cubic meter. And we say that the depth of that mass of soil is 1.45 meters. So by the time we factor it, we are going to have our value for our dead load. So we can say that the total ultimate load of the system, having factored both the live load and dead load, we're going to have 49.58 kilonewton per meter. All right, so the net upward pressure, we have the maximum pressure to be the net weight, having minus our gravity load. We assume gravity load, total gravity load is about 50 kilonewton per meter square. All we need to do is approximate 49.58. So when we solve that, we're going to have the maximum pressure at 239.3 kilonewton per meter square. And we'll have the minimum pressure to be 174.58 kilonewton per meter square. All right. Now let's look at the pressure variation. If you look at the pressure variation, it's a trapezoidal load, and we'll have it as 230 on one side. We'll have here to be 230.93 kilonewton per meter square. Let's call this one P1. On this side, we have P2, 174.58 kilonewton per meter square. All right, so we take the center of the footing. This is the center of the footing. From edge Q to the center is 1.25. Remember, the footing is 2.5 by 2.5 meters. So we have from here down to this point to our critical perimeter. So this point is our CP, critical perimeter. So from there to our critical perimeter, we have it to be 1.5 H according to our code. Remember, some code do have it as a 1.5D. So whichever code you are using, all right. So now if we take the measurement from the center of our column to the critical perimeter, 0.7125 meters. Now let's draw the pressure diagram. You can see from here, like we said before, the pressure is going to be more on the Z point. And if we draw it, we'll have it like this. Now we're going to get this value for the pressure because this whole area represents the area outside the critical perimeter, which we're interested in. So we're going to work out the value for the stress of the area outside the critical perimeter. Now these are the stresses. We have the boundary between P1 and P3. Of course, P1 represents the maximum stress. So all we need to do is to make use of a similar triangle to obtain the point. From this point down to this point, we're going to obtain it. There's a diagram here, 1.9. If you add up this plus this, this 7, remember, we're going to have 1.9625 from here down to this point, which represent P3, okay? All right, so if we solve it by similar triangle, we're going to have our P3 from here down to this point to be 174. From this height here is 174 plus what we got here to be 50.8 kilonewton per meter square. So if we add it up, we're going to have 225.3 kilonewton per meter square as our P3. All right. So if you check, you are going to see that the difference is not much. We have here to be 239.3 kilonewton per meter square. while we have here to be 225.3 kilonewton per meter square. So all we need to do is to have the average of these two so that we can use the pressure here to multiply our critical area outside the critical perimeter. Okay, so that is exactly what we have done here. Remember, we have this point. So we now come to the determination of our punching shear check. Having gotten this pressure that is acting on the area outside the critical perimeter, which represents our punching zone. All right. So we said that the critical perimeter is column perimeter plus 3 pi h. Our pi is 3.1428. We have the critical perimeter to be 501.5013.6 mm. Okay, so that is what we have for our critical perimeter. That is what we have for our critical perimeter. Now, I will say that the area outside the critical perimeter becomes the area of the entire square footing, which is 2.5 by 2.5 minus the area outside within the critical perimeter. And remember that that formula is the column size plus 3h minus open bracket 4 minus pi close bracket and open bracket 1.5h all square. Okay, so if we solve that to obtain the area outside the critical perimeter, we'll have that area to be 4527.900 mm square. All right. So that area, we're going to multiply that area by our pressure to get the pressure that is acting outside the critical perimeter. That's the pressure that will give us our punching shear stress. Okay. So we have that. So if we multiply that pressure by the area, which is this. So the pressure, which is 230 times the area, will give us the total load acting on that area outside the critical perimeter to be 105.048 kilonewton as the load. Okay, so having gotten this, we now need to obtain our punching shear stress. All right, so take note that where we were able to obtain other loads as other gravity load that are acting on the footing. This is an economic way of design. Of course, you can make use of the gross value without considering some of this load is the choice, whichever you wish to do, of course, but we just want to be a little bit economical in terms of the stresses that are acting, the net stress acting on the footing. So if you decide to ignore the whole of this load, you are still in order. Okay, so now let's go over to determine the punching shear stress. Shear stress, the punching shear stress is equal to the shear force at the critical zone, V over critical perimeter over effective depth. If we work that out, we are going to have our punching shear stress to be 0.6424 Newton per millimeter square, and that is less than the allowable shear stress, punching shear stress, according to our code, 0.8 FCU or 5 Newton per millimeter square, whichever is lesser. So we have our punching shear to be okay. So we can say that the section is adequate in punching. So our dimension for this footing, overall dimension becomes 2500 mm by 2500 mm by 400 mm deep footing. Okay, so this gives us the dimension of our footing. Next, we're going to check for the transverse shear. We know that it is 1.5 D away from the surface of the column. So we know that we've gotten our P3, but in this case, let's assume the P3 that we got from our punching shear. Remember, our punching shear is 1.5H. So the P3 gotten from there, let's assume it to be equal to our P4 in this case. So we're calling this one P4. So 1.5 D away from the surface of the column. So we'll call it P4. So we are using that same value for our P4. So if we take the average of that value, our P3 and our P4, we'll have our stress as usual. Okay, so we have the area to become the stress times the area to give us the shear force that is acting on that transverse shear region that is shaded. So remember, we need the shaded region. So the shear stress in that shaded region becomes 0.46, and it's lesser than our liable shear stress, which makes the section also adequate in transverse shear. All right. So the next phase we're going to look at is the design for moment. All right, so now talking about the design of the footing, we are going to look at the footing. We've divided the footing into two equal half, 1.25 meters on both sides. Let's call the center of the column to be O. So we are taking the cantilever part of it like we did in our previous design. So if we carry out the cantilever part of it, we can see the loads acting on it. Remember that we are taking the net load like we did from the load analysis. So picking the net load, we have 239.3 kilonewton per meter square, 174.58 kilonewton per meter square. All right, so this is a cantilever. Let's divide the load into equal half. Here at this point we have 174.58. If we pick at this center here to this point, it represents 33 kilonewton per meter square, while at this point here, it represents 32.5 kilonewton per meter square. All right, so if we add up the total UDL, this plus this, we'll have 207, and the moment at point O becomes 207 times 1.25, which times half of 1.25, and that gives us 161.7 kilonewton meter. Now the next is our triangular load, so that if we work that out, it will give us 17.18 kilonewton meter. Now the total moment at point O becomes 178.88 kilonewton meter per meter. Now we need to calculate the ultimate moment of resistance of the section from Bs8110. Ultimate moment of resistance of a section is 0.156 BD square FCU, and we have that to be 414 kilonewton meter, which is greater than our applied moment of 178.88 kilonewton meter. So the section is adequate, so we don't need any compression, any top reinforcement in this section. Of course, it's not common with slab. So we look for other factor, our K factor, and we have our L, our Z factor. So from now, we can work out the area of steel required. Now the area of steel, have the area of steel required to be Y20 at 150 centers in each way of the footing. All right. So this brings us to the end of the lecture. If you have any question or any doubt, you can please send your comments or write through my email. I'll see you in our next video. Thank you very much for watching. I remain your host, Engineer Baga. Stay cool.